we are going to go over the transport and metals. So we know that when we consider transport of metals, we need to look at the electrons, how the electrons travel through the metals. And for example, if we take sodium, sodium is a simple metal, and in it we have transport is described by Drude's model. So in this case, we can have Drude's model, and subsequently it is modified by the two rules. One rule is Mortensen rule, and another one is Heimheld. And we will look at these models together here. So in Drude's model, we can consider electron as a free particle that has a charge, and it is located in the electric field E. And in this field, we can have trajectory looking like this, and here we have it is deflected, or it is collides with some ions in the lattice. In this case, we can write down this equation for the motion of the electron, which is described as Newton's second law. So we have here dp dt on the left side, and the right side we have E times electric field, which is electric force, and we have here P times divided by T, which is momentum relaxation. So we have to solve this equation, but it is we can modify it with the case that we have here in the lattice ions in the sides of the lattice, and these ions in the lattice, they will not have much influence on the electron's trajectory. So what influences the trajectory of the electrons is the defects located in this lattice. And because of that, we can consider that Drude's model is a little bit not correct because of that. Now we can write down here this equation again. The equation that we wrote above is correct still, and we can solve it for P in equilibrium state. In equilibrium state, dp dt is equal to 0, so we equate to 0 this right side and solve for P. Now, to find out this current density, we can use this formula. Here, En divided by M times P, and we substitute the value of P that we derived above, and we finally find this for this density curve, which is equal to sigma C times E. Now, here sigma C is called conductivity, and it is equal to this expression here. So it depends on the relaxation time that we have to now look at. Now, in the case when we have electrons in the lattice, and we can describe them as having as looking as a wave, and they will have this wavelengths, which is called Fermi wavelengths. And for the Drude models to be correct, we have to use this inequality. So in this case, this Fermi wavelengths must be much smaller than the mean free path, and here dimensions of the system. So in this case, this Drude model will be correct. Now, if you look at the Drude's model, so a little bit different, and this is called Boltzmann statistics. Now we can find, remember that, for example, in 1 meter cube boson, we have 10 to the 28 electrons. So this is very large number, and we can use here statistics. So first time statistics was used in condensed matter by Boltzmann, and he considers here this distribution function, which is called the Boltzmann distribution function. And this distribution function shows possibility or probability of one electron to be at the coordinate r, radius vector r, and have velocity v at some time t. So this is our distribution function or probability function. So we can write down here this equation, that considers here this change of this probability distribution with time, which should be equal to the df/dt at collision. So here this will be described as a collision integral, and it depends on the relaxation of the distribution function according to so it interacts with lattice size, so it describes this lattice interaction. Now the first, on the left side, df/dt, we can write out using this equation, is from mathematical analysis, and here we have df/dt, which is velocity vector, and dv/dt is this acceleration vector. And we change this acceleration vector with this value here, where here E is the energy of the electron, which is equal to mv squared divided by 2. Now this df/dt collisions is described with this integral, where wv strict is a scattering matrix element. So we will see below that there are several types of scattering, and this wv strict prime depends on the type of the scattering. So first, in simplification, could be that wv strict is constant, and this is called constant relaxation time, and this constant relaxation time approximation. So this happens when we assume the probability to scatter towards other states is constant. So this approximation is valid for as long as we have these defects that will have short range potential functions. Now, if you look at the Boltzmann transport equation, so we substitute this expression for df/dt, which we write down here, and df/dt collision written with this integral. We can substitute here and in that above equation, and we will find this equation, which is called Boltzmann transport equation. So this looks as a little bit complex. Now we write down here that f equal to f naught plus delta f. Here f naught will be equilibrium part of the distribution of probability function, and delta f is non-equilibrium part of the probability function. Now the transport properties are governed by the delta f. So this non-equilibrium part of the distribution function. Now in the steady state, df/dt equal to 0, and from the equation 1 we find out this delta f, and the delta f looks like in this formula here. Now the first, there will be two terms. There are two terms in this expression for delta f. First term is called drift term, and the second term here is called diffusion term. Now in this case, ddr is a null operator, and it's written down here. So if we substitute diffusion part in the current, so for the current we have formula written like this. Current is density, and we can find out here this. We substitute delta f. If we substitute first part, drift part of the distribution function, and equilibrium delta f, we find out this drift current, which is written in this lines here. So we substitute here, and this here delta function here. And according to the delta function properties, we find this final expression for the drift current, which shows that here we can write down the coefficient in front of here as a conductivity, drift conductivity. So here is drift conductivity. It depends on the tau relaxation time, and also on the density of states at Fermi level. So again, this tau is very important in considering different types of scatterings. Now, if you look at the diffusion current looks like this here. So we substitute diffusion part of the delta f here, and final expression for the drifting current will look like this. Now we have here this coefficient in front of d and dr, which is called diffusion coefficient. Finally, we find can write down here this expression for current, which is written with this expression here. First part is sigma c times E is the drift drift current, and second is diffusion current. And we can complement this equation with this equation, continuity equation that describes change with time electrons concentration. Now these two equations form drift diffusion model, and they are cornerstone of the transport equation for the metals, and we can use them to find out current in these metals subsequently. Now let's look at the model for the charge transport and spin transport in metals. So here we can write down this relation for sigma c and dc, which is written with this expression here, and it's called Einstein relation. Now, if we talked about this matrix element, scattering matrix element, W', and we said that it depends on different kind of collision in metals. So first kind of collision here could be with impurities, second kind of with defects, third kind with phonons, and the fourth kind is this is electron interaction. So electrons can scatter on each other. So among them, the most important ones is electron colliding with impurities and the electron colliding with phonons. So let us look at these two kinds of scattering. First, we look at scattering against impurities. In this case, impurity potential function could be written with this expression here. So this expression here is the sum. We have summation on the impurity sides. And it looks like it has two parts here. First part is the electrical potential energy interaction of this site of impurity having Ze charge, and the electron that collides with it having electric charge E. And together with that, we can multiply this expression on exponential term, looks like this. So this exponential term shows us this how narrow we have here this potential function of the impurity. So it's called the Yukawa potential. Now, because of exponential term here, this impurity term is very could be short range. So its range is very small, and because of that, it will be acting not at very large distances. In this case, we can write down this impurity potential function, writing this line here, and here we have here this again summation on the side on the impurity sides here. Now, using this potential function, we can write down here this expression for the relaxation time. So here this expression for the relaxation time, and here Ne is the impurity concentration, and NEF is density of states of electrons at Fermi level. And according to that, since Ne and EF both are constant, we can have this tau constant value, having constant value. And because of that, we have constant relaxation time. And this corresponds to the approximation that we used before. Now, looking at this equation, we can see that as NEF increases, we have tau decreases. And this corresponds to the strong scattering here. Now, scattering at phonons has a formula here looking like this. We can use here second quantization, and according to second quantization, we can find two dependence of tau relaxation time on in this scattering. So T1 over T is proportional to T to the 5, or 1 over T proportional to T. So first case for temperatures much